So next we're going to get into some situations where we can easily compute some of these line integrals. The first very basic example just serves to illustrate that in the definition of our integrals, we don't really need any smoothness of gamma for everything to work. Let's see, if we have just any curve and I want to integrate just dx along gamma, well, it'll just give me the change in the x values along the curve. Why is that? Well, if I look at one of my approximating sums, I'll just get a sum of a bunch of delta x's, and then this will be a telescoping sum, and so I'll have something like xt1 minus xa plus xt2 minus xt1, and you'll do that all the way down the line and see that you just get x of b minus x of a. And so for all of our approximations and all of our taggings, there's no function, so the tagging doesn't matter. We always just get the change in the x values. Similarly, for dy, you get change in the y values, and integrating dz, we just get just change in the values of gamma. Okay, well, this just shows the curve doesn't necessarily need any smoothness, but most often it will have smoothness in the examples we're interested in. So let's say we have gamma defined on the interval AB, and it's C1. And we usually include this condition that its speed is never zero, or its velocity is never zero, so gamma prime of t is never zero. And such a curve we'll call a C1 curve. I think some books, like Rudin, calls this a path. And the main thing to know about C1 curves is that we can easily compute the integral of a one form along a C1 curve just using a standard real integral. So at this proposition, if I have gamma as a C1 curve and a and b are continuous along gamma, then the integral of a dx plus b dy along gamma is just basically you view x as x of t, and so dx becomes x prime of t dt, and dy becomes y prime of t dt, and we just integrate t from a to b. So this, our integral of the one form along gamma, can be computed just by a real integral from a to b of a of gamma times x prime of t plus b of gamma times y prime of t dt. And for 1,0 forms, you can write something similar. So you're just replacing z with gamma of t here. And so dz becomes in the integral gamma prime of t dt. And we just have a of gamma times gamma prime dt. Now I do want to say a little something about the proof, but I don't want to take too long because it's more important to get to examples. But how do you prove this? Well, the basic idea is you have to compare approximating sums to these real integrals somehow, and one way to do that would be to compare them to Riemann sums for these real integrals. So in an approximating sum for the line integral, I'd have an expression like a of zj star times delta x, and in a Riemann sum for this integral, I would end up with expressions like this, a of zj star x prime at a sample point times delta tj. And basically we can compare, or we can use the mean value theorem to represent x of tj minus x of tj minus 1 to x prime of some other point, delta t. And so we'd end up with bounding this by a times the supremum of the difference of x prime of t and x prime of s, where t and s live in the same small interval. And we can control this for small delta t's using uniform continuity. So I could make this kind of small over all of the intervals, so small independent of j, and that would give me a way to compare approximating sums to Riemann sums, and then you could just refer to the theory of Riemann integrals to show that we were actually tending towards the Riemann integral here. Now let's get to examples. So this first example will just be something that we already basically learned about on the go, which is integrating functions on a circle. So this will be a way of parametrizing the circle of radius r centered at z0 counterclockwise. So I have t going from 0 to 2 pi. And so an integral of a continuous function f that's defined on this circle will be equal to this Riemann integral. So I'm just replacing z with gamma of t in here, and I replace dz with gamma prime of t dt, which in this case becomes r I e to the it dt. And this agrees with our earlier definition when we defined these integrals over circles. Okay, and let's do a more concrete example. Let's integrate z dz over the interval, not interval, line segment from z0 to z1. So we can parametrize the line segment as we've done before, 1 minus t z0 plus t z1. And, well, we take the derivative of this, and we get minus z0 plus z1. And we put that into our formula, and we get gamma of t right here. Gamma prime of t is z1 minus z0. And then you just have to do the basic calculus to compute it. So this term comes out front, and you have to integrate this with respect to t. I won't go through the details of that, but you end up with z1 minus z0, 1/2 z1 plus z0. But you end up with a very familiar expression that, looks just like we were integrating x0 to x1 of something like x dx. And we'll see that it's no coincidence very soon. On the next slide, we'll get into piecewise C1 curves and some important formulas.